Key to creating this visualization is scientist Jeremy Schnittman at NASA's Goddard Space Flight Center.
All of the ways that we model black holes with math and equations and computers, it all kind of falls apart at the edge, at the event horizon, because everything either goes to 0 or infinity, and it makes it really hard to solve the equations. So this year we wanted to try to solve that problem, to get around all of the mathematical challenges at the event horizon and take those cameras and take those visualizations inside. It was all this new physics that we were exploring, and that's what we do as scientists. We love to go beyond and learn new things.
Jeremy's computer code applies the laws of physics, including relativity, to individual photons and tracks their paths.
To get really just the photons that hit the camera, we have to go backwards in time. We start with the photons at the camera, and then we just follow them backwards to see where they came from. Fortunately, all of the equations of relativity and physics in general are time reversible, so they work basically the same forwards and backwards. But if there's one place in the universe where they don't behave so well, it's at the event horizon, because things don't go forwards and backwards across the event horizon. So those kind of conceptual things I had to be really careful and think carefully about. All of this, of course, starts with just brainstorming and a storyboard, kind of hashing out what this might look like and what we hope it will look like. Then we have to try it again in kind of low resolution to get a couple more sophisticated snapshots to see how it will look. And it's an iterative process that both involves the technical problems that I'm trying to work through, figuring, oh, well, this isn't working because of an equation, and then feeding that back through the artists and the communicators that will help say, well, this isn't working from a story point of view.
Jeremy worked with astrophysics science writer Frank Reddy and video producer Scott Wiesinger to refine and construct the final videos.
That's actually one of the parts of the problem I like the best, this teamwork between the technical and the narrative part of it. I got to really invoke my Kip Thorne interstellar physicist-artist combination, right? The strict physical reality is that the camera's just going faster and faster as it gets closer to the black hole, which would make it realistic but very difficult to watch. It would just go zoom, and you're done. And of course, all the interesting stuff happens at the zoom, at the end. This is one of those places where you have to choose between the strict physical reality and the fact that you're really trying to tell a story. So we had to take our artistic license and slow down the camera to help share that exciting experience. To get a feel for what it's going to look like, we start off with a low resolution image or maybe a few snapshots. And that sort of level of calculation is not too difficult to do on a laptop computer. Try it, it doesn't work. Try this, it doesn't work. Fix this, it works. Okay, now that we've got something that basically works, then we need to ramp up the resolution, make a whole lot more frames. And at that point, the laptop computer is really not powerful enough if we want to make this video in less than 100 years. So at that point, we essentially take the same computer code and port it over to a supercomputer that can run many calculations all at the same time.
Jeremy loaded his code on the Discover supercomputer at Goddard. With 213,000 cores, Discover can process code at 8,280 trillion floating point operations every second. Data scientist Brian Powell helped load and run Jeremy's code on Discover. The initial run required about 10,000 CPU hours and generated 10 terabytes of raw data.
It's a different job for each frame, right? We're making one image, and that takes a few hours, but then we have tens and tens of thousands of these frames to make the movie. And then the last part is the Discover generates all of these numerical files, just lists of numbers, and I have to pull those back and convert those then into images. So I have a couple of the last steps of converting just raw numbers into JPEG files of images, also just running on my personal computer, because that's where we can kind of play around with them and preview them in an easier way. Putting all that together, we would find some weird properties. And you have to go back and figure out what the problem was, work it out again on the local computer, and think you've got it fixed and put it all back through the Discover cluster again.
To show everything an observer might see on the trips into or around a black hole, Jeremy generated 2 map projections of the entire sky. One worked within standard 360 options, and the other, called a mall-wide projection, is often used to show the sphere of sky from astronomical observations.
And then there was really a third one that we worked on, which was the zoom-in, right? So we also have these zoom-in frames that are, I would say, more like a conventional camera, a small field of view right in front of you. And that was great for picking out some of the really cool relativity features like the photon rings. As we both zoom in with the zoom-in frames and physically zoom in, bringing the observer closer and closer to the black hole, you get closer to this really cool feature of the black hole called the photon ring. And this is where light gets bent by the black hole 360 degrees around. And then beneath that, there's another set of photons that got wrapped around twice by the black hole, 3 times. Like, it just goes forever and ever. Ring after ring after ring as we skirt that critical surface, getting closer and closer to the event horizon and the singularity. We're seeing more and more of these light rings, and also copies of the accretion disk and the galaxy get bent around and around the black hole, and we're going to see more and more copies of basically the entire sky. Every loop around is another copy of the galaxies. And now we're almost hitting the singularity in the front, and everything just right at the end.
Even for someone as familiar with black hole physics as Jeremy, watching the new visualization led to some unexpected discoveries.
Completely genuine surprises. We see at some point, very close to the end, we see like the sky almost shrinks. And we figured out that was because of some of these relativistic effects of the whole sky getting pinched towards you as all of those photons hit you in the face.
Not all the surprises were welcome. After Jeremy produced the first full batch of zoom frames, a strange jitter was apparent.
These jitter problems were the kind of things that by definition happen at the end, because we only saw them in the really high resolution, smooth videos where you're getting a lot of frames right next to each other. And what we think was happening was that you're basically stepping the camera forward in time by, big steps, and this part in between those steps wasn't perfectly smooth. So it was like literally the difference between going up and down stairs and going on a slide. And we were taking these steps, which were kind of almost like jerking the camera back and forth. So we had to come up with a way of making those steps into a nice, smooth ride. And then at the very end, where it was almost like the inescapable jitters at the singularity, at the center of the black hole. This is where even our best equations have trouble. There are matrices and inversions and integrals that just struggle with the infinities that happen at the center of the black hole, and there's almost no way around it.
With Black Hole Week 2024 looming, Jeremy and Brian Powell rushed to solve the issue of the jitter and generate new, smoother frames for the final videos.
We've done this before. We've done this 3 or 4 times before for Black Hole Week. We know the deadline. We know when we have to get everything done. We started over 6 months in advance because we knew we had to get all this stuff done in time. And yet, there's always that rush at the end. And it's stressful, but it's also fun, right? Because it's like real life physics. In my particular case, it was even more exciting, because I was traveling out of town for a family wedding that weekend. So I was like in this cabin in a location wedding in the middle of nowhere, trying to get internet, working with Brian on the Discover cluster, working with Frank and Scott, trying to get the frames all set. So it was a lot, but it was so worth it, because the final product was just tremendous, I think.
Despite all the math, science, and computer